well, is it working? Is it not working? Anyway. Okay, so let's talk about the mark. My suggestion would be there aren't so many people who need a mark. So my suggestion would be for everyone to give a talk and prepare notes in LaTeX. What do you think? Okay, so. Ну, курс все-таки довольно продвинутый. Я не думаю, что здесь можно, что здесь можно настрочить такой набор стандартных задач. Okay, so let's say. Well, let's say plan A. Talk plus notes in LaTeX. Handwritten notes will not do. You need to really feel it, and the best way to feel it is to prepare a set of notes in LaTeX. And there will be, there isn't, but there will be a web page. And we'll post the topics on the web page. Okay. Well, I think this is it as far as technical issues are concerned. Is there anything else we need to talk about? Well, yeah, it looks like we can. Yes. Well, there is one thing: surgery theory. Let's talk about that. Surgery theory, what is it all about? Well, let me just mention one problem which surgery theorist sort of solves. It's not the only one, but it's well, it sort of gives one an idea of what this theory is about. So suppose we have a Poincaré. A Poincaré duality CW complexes. A Poincaré duality CW complex. Now, what does this mean? Well, it means precisely what it says. Well, let's assume for simplicity that the let's assume, for simplicity, that X is simply connected. Then then we require that there should exist a fundamental clause such that the cap product with it should be an isomorphism. Well, this is a reasonable homotype invariant analog of a smooth manifold. Now, we want to define the manifold structure set. Of M. Sorry, not of M, of X. Is the set of all couples M a smooth manifold, F a homotype equivalence between X and M up to an equivalence relation. What is the equivalence relation? Well, we say that a couple MF is equivalent to M prime F prime if and only if there exists a cobordism between M and M prime and a homotype equivalence between this cobordism and x cross 0, 1, which, hold on, no, let me write it in this direction. Because here we consider maps from x to m, so I want to do the same here. A cobordism which is a homotype equivalent to x cross 0, 1. So in particular, it's an H cobordism. What's an H cobordism? We'll shortly talk about that. Which restricts to F disjoint union F prime. And the question is this manifold structure set, what is it? Is it empty? Is it non-empty? If it's non-empty, then how large is it? And the answer is well, it's not really an answer. The answer is given by a surgery exact sequence, which is an exact sequence of pointed sets. Unfortunately, there is no natural group structure on this thing, so the exact sequence tells us something, but it works. It doesn't work as well as it does for groups. Well, so hopefully we'll get there. Well, not very soon, but let's say. The plan is to cover this material in the first third of the seminar, and then we'll talk about complex manifolds and well, a little bit about singularity theory, and after that we'll talk about cobordisms and more precisely about PL and topological cobordism rings, which are computable, but they're not the same as the smooth cobordism rings. So this is. So this is this was an example of the sort of things we'll do in part 1. Part 2 will be about complex manifolds, and part 3 will be about cobordism theory. And by the way, here is the first topic which I want to advertise. I'll put it on the web page, but I might as well mention it now. In the last semester, we sort of wandered off towards chromatic homotopy theory in the end of the seminar, and we didn't have the time to discuss properly the oriented Bordism ring, or in other words, MSO of a point. But still, this is something I would like to talk about, because before talking about PL and etc., it would make sense to do the easy case first, which is the smooth cobordism ring. So it's a good topic for a talk. Anyway. Well, that's the plan. No, well, unless someone volunteers to give a talk. But I must warn you, this example uses gauge theory, which we will not have the time to discuss properly. Okay, are there any questions? Well, for example, suppose we want to know whether or not a Poincare duality complex is homotopy equivalent to a smooth manifold. Well, this is equivalent to saying that M of X is not empty. Well, if we have a homotopy equivalence in one direction, we have well, you want it to be contravariant. Well, yes, this. Yes, but what's the group structure? Yes, but what's well? Suppose I keep x fixed, and I want to multiply two arbitrary maps. What do I do? Are there any more remarks, criticism? Okay. Now, all of this, including surgery theory, is based on Morse theory. My plan for today was to talk a little bit about Moore's theory and sorry about that. Yeah. And maybe some of the things I wanted to say are already familiar to someone, but let's see. Well, does everyone know what a Morse function is? You do know, or you don't know? You do know. Okay, I'll ask a different question. Are there people who don't know what a Morse function is? No, there aren't. Okay. Now, the next question. Does a Morse function suffice in order to write down the Morse complex? What do I need to write down a chain complex which calculates the shall we say integral cohomology groups of a manifold? Okay, so let's say I have a manifold and a proper Morse function. Well, suppose the function is bounded below. If you like, you may assume the manifold is compact. Does having a function suffice in order to calculate the homology? The answer is no. In addition to a function, we need to have a metric. Why? Well, let's see. Well, suppose the values of f on the critical points are all distinct, and these are called critical values. Now we want to We want to relate the manifolds with boundary the manifolds with boundary, which are the Bray images of minus infinity y naught minus epsilon, and the same for y naught plus epsilon. So how are these related? There are two things which one can one can prove. Well, first of all, after passing through the critical value, we get m y naught minus epsilon with a k cell attached to it up to homotop equivalence, where k is the index of y naught. Does everyone know what the index of a Morse critical point is? Grisha, is it the number of the pluses or the number of the minuses? Yes. Okay. Now this is up to homotop equivalence. Now, suppose I want to know this thing not just up to a homotop equivalence, but up to a diffeomorphism. What do I do? Well, I need to attach a k handle along a map psi. What is psi? What is a k handle? Well, I'll draw those on this board. Okay, it really is a fancy board. You see? Okay. On the other hand, it's quite difficult to wipe the board. Anyhow. Well, what are the maps phi and psi which are used there? Well, phi is just a map from from the boundary of the K cell to m y naught minus epsilon. Now, what is a K handle? Well, it's just the product of two disks. Let me draw a picture for K equal 1. So now I would like to use some other color, and it looks like we don't have any. Oh, yes, we do. Автограф, хорошо. Популярность просто пугает. Значит,
так, вот здесь вот можно расписаться?
Хорошо. Но на самом деле я, собственно, сегодня и завтра буду практически целый день.
Да, ой, как здорово. Я к вам завтра подойду, мы с вами обсудим фото, хорошо? Как что делать?
Хорошо, да.
Спасибо большое.
Не за что. Well, so let me draw the K handle for K equal 1. Now. And I'll explain the terminology. Well, first of all, the K handle contains the K disk across the center of the n minus K disk, and this thing is the same as this thing is the same as the K cell, which we attach. Now, the boundary of this is, and this thing is called the core of the handle. Now, the boundary of the core is called the attaching sphere. And is there a green chalk? Nope, nothing. Well, okay, I'll use the white one. Now, Apart from the core and the attaching sphere, I will also need the belt sphere, which is the same as n minus. Which is the same as 0 cross S n minus k minus 1. We will frequently need to see whether the attaching sphere of one handle intersects the belt sphere of another handle. So this picture will appear several times in the sequel. Let me just put it up there. No, I still have some room on this board. Does the picture make sense? Okay. Now there is one. Oh yes, yes, yes. You're right. What is the map psi? Psi is a map from S k minus 1 cross d n minus k to again to m y naught minus epsilon. The domain of psi is the area shown in this picture. So phi is defined on the pink points, and psi is defined on a neighborhood of the pink points. Does this make sense? There is one issue. What do? I take this this thing which is not really a manifold, and then I take some subset. I take this map psi. Now, what do I get after I attach the handle? Well, I get a manifold with corners, but manifolds with corners can be smoothed. I don't want to explain this in too much detail today. We'll talk about it later if necessary. Basically, what this means is the way it's written is it's just a topological space, but it has a unique. This space has a unique structure of a smooth manifold. Okay. Are there any questions? Now, I've just said something about having a metric. Where does the metric come in? Yes. We need the metric when we do the following thing. So we've just seen what happens when we pass through a critical point. But suppose we don't pass through a critical point. Suppose we have y0 and y1 such that the line segment y0, y1 has no critical points whatsoever. Then the manifolds are in fact diffeomorphic. Sorry. And it is here that we use the metric. Well, because after I have, for example, if I use this, I want to deform the attaching map so as to get a cellular map. And no, hold on. Well, we do need to get a cellular map, but a metric will not help us to get one. I don't have any short explanation except except that these isomorphisms, which we use to construct a complex using the Handel decompositions, do depend on the metric. Say again? No. The complex itself, the homology doesn't depend on the metric, but the complex itself does. But I don't have a simple example which maybe if you ask Petya Pushkar, he will give you an example straight away. Anyway, are there any more questions? Okay, now where was I? Oh yes. Let's prove. Let's first of all. When are we supposed to finish? To finish the first half. 15 minutes. Okay. Let's prove. Let's prove something. Let's prove the Morse inequalities. Well, let's take a field. Let's take the ith beta number, call it Bi, of M before okay, before okay, let me finish the notation. Bi, the ith beta number. Ci, the number of the number of the critical points with index I. Now, does anyone remember what the Morse inequalities say? Yes, but in fact, they say a bit more. What you've just said basically says that the homology, the rank of the homology vector space is always less than or equal the rank of the corresponding component of the cellular chain complex? Well, it's sort of obvious. There is a less obvious Morse inequality. Well, it's a little bit less obvious. It's still obvious, but a little bit less obvious. Well, let me write it like this. So on the one hand, I have I can take this expression, and on the other hand, I can take the same expression with Ci. And the Morse inequality says that one of them is greater than or equal than the other, but which? Which is greater than or equal than which? Yes. Well, there is a slightly tricky part here. Well, first of all, if the critical points are ordered by the index, then this is indeed obvious. Let's okay. I'll use this board. Okay. But suppose suppose they're not. Then what do we do? Okay, I will put the board here. By the way, does anyone know the correct way to call functions such that if we have two critical points, then two critical values, one less than the other, then the index of the critical value, which is less than the other critical value, is less than the index of the other critical value. Okay. Let's well, since none of us knows the correct terminology, let's just invent some. Okay. Now, yes. So suppose we have a Morse function with this property. Then we we can construct a sequence of CW complexes such that MI is well. Let me say this. Okay. Alpha I, where alpha I is increasing. No. In other words, we start with some number of zero cells, which of which there could be many. We don't know. Then we attach some number of one cells and so on. And it follows from this that there is a chain complex. Which calculates the homology of M. Such that the rank of capital Ci is small ci. And this already implies this this inequality. Why? Well, the expression ci minus 1 plus etc. plus minus c naught is the Euler characteristic of the Euler characteristic of the chain complex, which is obtained by forgetting setting all yes, it's yes, because the Euler characteristic starts with the Euler characteristic counts C naught with minus 1 to the ith. Okay. The Euler characteristic counts C naught with a plus. Yes. Now, this is the Euler characteristic of this chain complex counted using using chains. But we also can calculate the same Euler characteristic using homology. And what are the homology groups of this complex? Well, almost always they are the same. The same as the homology groups of the original complex, but in degree I, let me say the rank of hi of c I star is okay. I'll write two numbers, and then we'll see which one is larger than the other one. So I have the rank of this homology group, and I have the rank of this of hi of this thing. Now, which one is larger? Is it this one or this one? Well, let's see. The chains, sorry, the cycles are exactly the same. But this complex may have boundaries in degree I, and this one cannot. So, which one is larger? So this one is larger than or equal this one, because the cycles are the same, but this one has more boundaries than this one. Okay. When are we supposed to stop? 5 minutes ago. Okay, so my claim is by looking at this inequality, one immediately sees that this expression is greater than or equal than this expression. Okay, are there any questions, comments, criticism? Okay. Well, I think we need to have a break, and I also suspect we will need to move room because it looks like there's one seminar here in a few minutes. Когда ты понимаешь, сейчас начнется еще? Да. Грандиозно. Так, хорошо. Слушай, может, ты посмотришь расписание? Что за обман? Какая обман? Значит, Нина сказала, что у нас две пары. Что здесь будет? Здесь семинар лампа Горинов. Хорошо. Так, ну хорошо, да. Я не знаю. Ну, выключай, если бы я знал, как выключить. Ты знаешь, как выключить? Ну, в общем, возможно, нам придется сейчас куда-то переместиться, но куда неизвестно.
Нам не сообщали, что у нас что-то куда-то переносится.
Какие методы, к сожалению, бывают?
Всегда бывает.
А у вас 108-я по расписанию.
Ага.
А вот 108-я у нас 108-я?
Ну да. В сетке расписания у вас 108-я.
Здравствуйте, была эта. В прошлом семестре была эта.
Хорошо, сейчас давайте найдем